My name is Fulton, and this is my intelligent remote lighting system for my graded Unit 2. Today I'm going to discuss with you my circuit which has been created for a newly developed industrial estate in Glasgow. I've been asked to come up with a lighting circuit which should be used within bus shelters and recreational area shelters in the Glasgow area. The system should provide a long-term sustainable solution, and it should also focus on Scotland's 2020 route map. The 2020 route map should provide 100% of Scotland's energy from renewable sources, either from wind or solar power. The client has requested the design and build of a lighting system for use within a newly planned industrial estate near the Glasgow area, which is set for completion in February 2016. The lighting system must provide adequate lighting for bus shelters and recreational shelters for the occupants, with some consideration for energy efficiency. All new developments in Scotland should have a clear focus on being as energy efficient as possible, within budget of course. The 2020 route map for renewable energy in Scotland update has a set goal for Scotland to have a renewable energy capacity to support 100% of Scotland's energy demand by the year 2020. To conform with this, the circuit produced will be as energy efficient as possible to aid in the attempt to reach these goals. Although on a small scale, this also reduces CO2 emissions and subsequently operational costs. The specification for this report has changed throughout the research and build stages, as ideas have either been accepted or rejected, a list of which follows. The system must provide sufficient lighting of approximately 1,650 lumens at between 6,500 and 7,000 Kelvin. It must be able to be powered via a renewable energy source if feasible, with an output supply of 12 volts DC. The system must be low maintenance, incorporating long life LEDs and robust components. Electrical safety is paramount. The lighting system will be supplied with a fuse to protect against overload and short circuit. It will also have vandal-proof fixtures and fixings used to prevent against public tampering. The occupant safety. The lights should remain on for a period of time after the occupants have left the vicinity. This ensures a higher level of safety and security for the occupants. The system should have a minimum IP rating of 54, which protects against dust and water spread from all directions. The lighting system must be designed to operate within the UK normal climate parameters of -5 degrees centigrade to 35 degrees centigrade. The research and development for this project followed a very simple strategy. Initially, generate ideas. From these ideas, pick the best, and then move them over to a simulation package. Simulation was done using Multisim. Multisim could show you how the circuit would operate. If it would operate, it would also give you the voltages, the current and the power used within the circuit at various points of the circuit. After the design stage was complete, we would then move to the build stage. The build stage consisted of building on breadboard. If successful, then it could be moved over to Veroboard. However, Veroboard was the last stage. After it was built on breadboard, we would move over to the testing stage. The testing would again test the power, it would test the voltage and the current. These results could be compared with the results of the design stage. They should roughly be the same, however there is a small degree of error. After that, we then moved on to the client check. The client check is just simply a meeting between myself and the client to sign off any ideas that were okay. The main restrictions of the project was the actual amount of time that we had to build the circuit from the design. We were given our components in March, and that allowed 2 months for us to get this built on breadboard and then finally onto Veroboard. 2 months sounds like a lot of time, but it was actually not. If you work it out, that's 8 weeks of class time, and that's 2 hours, so it's 16 hours to get this built. So needless to say, a lot of the work was completed at home. My sheer lack of electronic knowledge had me at a standstill. I had to research everything from Google, YouTube videos to learn how to solder, even how to use a breadboard. From then I progressed. Once the circuit was built and we got into the report stages, then the shelter location was a key factor. We're looking to use a renewable energy for the shelter, so whether it's solar power or whether it's wind turbine, both of which require the shelter to be located in a specific area where the sun will meet the solar panel for a full day's daylight, or where the wind can hit this turbine to rotate it to get maximum energy from it. And then finally, the restriction of the cost. We were given £30 to build the circuit. One of the key project requirements was to offer the client 3 solutions that were all capable of producing the same end result. This was in the form of power. We had the option of solar power, wind power or grid power, and we came to our conclusion on this through the feasibility study. The purpose of the feasibility study was to look at all the parameters of the circuit and to see what power supply could produce these the best. So when we talk about the electrical parameters, we're talking about the supply voltage. We'll be looking for a 12 volt supply for this type of system. The maximum voltage that the circuit could cope with is 15 volts and the minimum voltage would be 5 volts. The output voltage would be 12 volts DC, however the circuit could cope with a minimum of 9.9 volts due to the voltage drop across each LED. The environmental parameters looks at the daylight hours. Daylight hours looks at how much of the actual natural light can then get to the solar panel. The operating temperature, so whether it's a winter month or a summer month. And then waterproofing, whether the system or the casing would have to be IP rated. We then look at the physical parameters, the construction of the build, how well it's built. Then we look at the size, how much room is it going to take up, how heavy will it be, then the resilience, then how much noise would be produced, and finally how much light could be generated, the illumination. We then move on to the operating parameters, which looks at the safety of the build. We then look at the circuit operation, how well it can operate using those conditions. For instance, if it was solar power, the operation may be affected if there's not enough light. Then, operating range. This looks at how long a distance that a person could be detected from the shelter. Then exit lighting, how long the light would stay on for once someone leaves the area. And then finally we look at the maintenance. Maintenance, we want it to be as low maintenance as possible. So depending on what power source we use, that could be a major factor. If a problem was to arrive, then the components should be changed easily. The first option of solar power system would be allow the occupants flexibility in terms of shelter and daylight locations throughout the industrial estate, as both the roof space and light location can be positioned to ensure they are exposed to the maximum sunlight. This is a key point and it leads to the efficient system that will not lose power in winter months when sunlight is at a minimum. A power storage facility will be needed and that will be capable of offering an ample amount of power to operate the lighting system that would be required. This system storage may be in the form of batteries that are accessible when required. The solar system may be linked back to the grid so that any excess energy that is generated can be fed straight back onto the grid. This contributes to Scotland's total energy generation via renewables. We then look at wind power. The second option of wind power system offers another source of renewable energy. The end result of this type of system would be similar to that of the solar powered option. However, attaching a small turbine to a shelter could prove difficult due to the dangers associated with the rotating turbines and the planning permission required. Installation costs would also be greater than that of the solar, as heavy duty fixings would be required to mount the turbine safely to the shelter. The location of the shelter must allow for a maximum wind to pass through the turbine. This also depends on weather conditions and wind direction. Although it may be somewhat difficult to accommodate this type of system, the efficiency of the type of installation may be worth initial costing, as it would generate more than the required levels of powering the lighting system and would feed back onto the grid, same as the solar system would. And finally, we've got the option for grid. The option for grid power is entirely possible, as the industrial estate is still in the early design stages and has sufficient time before construction would commence. Although it was clear from the project brief, the client interactions that this was not the preferred choice, it still proves a suitable option due to the high reliability and assurances offered. The power supply of the circuit would also have to incorporate a step-down transformer from 230 volts AC 50 Hz to 12 volts DC. This is an additional expense alongside the cost of having power supply to the systems. This option does not allow the project to contribute towards Scotland's renewable energy targets for 2020. As it can be seen, the scoring on the feasibility study is as follows. We looked at size, strength, weight, ease of installation. We looked at safety, sensitivity, range of operation, power consumption. We looked at nuisance triggering, weather conditions, and then we were presented with a final scoring. Solar scored 103, wind scored 84, and grid scored 90. The scoring process falls in line with the expectations of the client and myself, and we'll be going with solar power. So, a solar powered intelligent remote lighting circuit was selected as the most suitable option for the project. This is a vast improvement in currently used lighting systems used today in bus shelters. Feasibility study identified the solar option as the strongest candidate in all categories, although the grid was a close second. The solar lighting system will be able to provide a renewable supply of energy that exceeds the required power needed for the lighting system to operate, and it can be supplied straight back onto the main grid. As the lighting system will be a self-contained circuit, installation should be straightforward, taking less time to install than wind or grid power sources. This saves in costs and allows for the lighting to be implemented much more quick. The lighting system and supply may even be used on existing structures if that's necessary. Although the initial cost of solar versus grid may roughly be the same, solar will more than pay for itself by never having an energy bill. It is a greener alternative to traditional lighting, which coincides with the 2020 route map's targets. The low cost involved and essentially maintenance-free nature of the project makes this selection the best for the client and for Scotland's efficiency. So now we're going to have a look at the actual circuit and the main circuit components. In my circuit, I use a voltage regulator to step 12 volts DC down to 5 volts. I use a PIR for detecting presence in the bus shelter, which will read a little pulse voltage to a transistor. We'll use a light dependent resistor which detects the light. We'll use a timer which will be used as a comparator. We'll have the LEDs which lights the shelter, and then we'll have transistors which we'll use as amplifiers and switches, and then finally a capacitor which is used to store charge to power the LEDs once someone has left the vicinity. As it's a solar lighting circuit, I had to use solar panels in order to generate the supply voltage. I cut up some of the solar panels off of my garden lights and soldered them together to make a solar panel. This solar panel did conduct electricity and output 15 volts in good daylight and then around 5 volts in not so good daylight, but it just was not operating as it should. I had to look for another option for solar, which I'll show you on the next slide. As you can see, I have bought my own solar panel now. I had to cut off the ends of the solar panel to make these clips. These clips are then compatible with the solar charging circuit on the right hand side. This was not my circuit, of course, I had to borrow this. So what would happen now is the daylight would go into the solar panel, it would be converted into energy. The energy would flow through the cables then into this little circuit. This little circuit has a series of diodes in there that would stop the circuit and the current and the voltage releasing back from it. It then feeds from that into the battery, charging a 9 volt battery, and it's this 9 volt battery that we're going to use as the supply. And this also coincides with the detail that I was talking about earlier with regards to storing the power generated from the solar panel. When it came to building the prototype onto breadboard, I tried to fit the whole circuit onto one breadboard. This was extremely difficult and looked very messy. It was hard to tell what component connected where, and when it came to testing, it didn't work. So trying to resolve that was extremely difficult. It was at that point then we decided to split it into 3 separate circuits. A PIR circuit, an LDR circuit and an LED circuit. What we're looking at here is the PIR circuit. This was the first stage. The PIR is connected there. As you can see at the top is the little black node. We were able to get this operational. As you can see at the bottom, there's 2 blue LEDs. When the PIR was operating, there was no visual to see if it was operating or not. It had to be tested via a multimeter. By adding in these LEDs, when motion was detected, it would light these LEDs up and it gave a visual identification that it was operating successfully. After the PIR circuit was successful, we moved on to the LDR circuit. Again, there's no visual to show that the circuit is working successfully. So we had to connect it onto the LED, which you can just see at the edge of the picture, and the LEDs lit when this was successful. Of the 3 parts of the circuit built, this was the easiest. As you can see from the picture, there are 3 LEDs in series with an LED resistor, and there is 3 rows of these. It constitutes 9 in total with 3 resistors. These were able to be tested by connecting a 9 volt battery across the positive and negative terminals of the breadboard. Throughout the build stages of the circuit, several changes had to be made to get the circuit operating as we wished. Firstly, the Zener diode was being used as a voltage regulator, which was stepping down the 12 volts DC to 4.7 volts DC. However, in doing this, Trying to get rid of such a large amount of energy, it was being dissipated as heat through the zener. The zener was getting extremely hot, and when I touched it I burnt my finger. This was a hazard, had to be changed, so we decided to make a safer option of an IC7805 regulator. Secondly, the number of LEDs we wished to start with was 21. This was deemed completely unnecessary, as we just needed a demonstration, so 9 LEDs was more than sufficient to show the light levels required. Because of the change in LEDs, the resistance values of these resistor LEDs, or LED resistors, needed changed also. They went from 500 ohms to 300 ohms. The capacitance of value that we had originally was 470 microfarads. According to calculations, that should have lasted around 40 seconds, but in actual practice it lasted more around 1 minute. This is far too long. We were only looking for approximately 30 seconds for the lights to remain on after the occupant had left the area. As detailed earlier, the circuit was split into 3: PIR, LDR and LED. Again, as stated earlier, an LED was added into the PIR circuit, so there was a visual to show that the PIR was operating. And then again, as stated earlier, the solar supply was changed. We originally used solar panels cut off of the garden lights round the back, but this was not operating, so I had to actually buy my own solar panel. The purpose of the 7805 regulator was to lower the voltage down to 5 volts and to maintain this 5 volt output voltage regardless of the input voltage changing or the load resistance changing. A PIR sensor is a passive infrared sensor, and what this little thing does is it detects motion through heat, temperature, and it converts this heat into an electrical triggering pulse. This triggering pulse can be used on the circuit for different reasons. On my circuit, it gets amplified by the transistor, which switches the other transistor straight down into my LED circuit. Once no one is present, it deactivates and no pulse is triggered. The LDR is a light dependent resistor. Effectively, this is a variable resistor which is reliant on light conditions. In low light conditions, then you'll have a very high resistance, and in high light conditions, you'll have a very low resistance. The resistance ranges from 400 ohms to 1 mega ohm. The IC555 timer is a very small integrated chip. It has very detailed internal circuitry which allows it to be used in several ways. It has 8 pins on it which can be configured in several different formations to achieve different types of circuits. It can be used as an astable multivibrator, it can be used as a monostable multivibrator, or it can be simply used as a comparator. In my circuit, it will be used as a comparator in order to allow the output to switch. Here we have an LED, which is a light emitting diode. Basically what happens is electrical current flows from the positive to negative terminal. The diode inside lights up. It lights electronically without wasted energy, as minimal heat will be produced. This is an image of my final circuit diagram. It should be noted at this point that there was no PIR sensor on Yenka, and a 10k potentiometer had to be used in its place. There was also no 7805 regulator, and a 4.7 volt zener had to be placed. I will now go over the operation of my circuit. The PIR sensor will detect the presence of a human body by sensing the occupant's body heat and converting that heat into an electrical triggering pulse. This pulse activates transistor 1, which is an NPN transistor. This amplifies the signal, which allows transistor 2 to switch on. This is a PNP transistor. This part of the circuit may energise but not operate the LEDs, as this is dependent completely on the LDR resistor. The IC555 timer is configured as a comparator. The LDR and 470 ohm resistor values are compared for generating an appropriate output through pin 3. As long as there's enough dart over the LDR, then pin 2 of the IC555 remains high, and this keeps the output pin 3 high also. In other words, it allows current to flow. This high output at pin 3 keeps the transistor 3, which is an NPN transistor, active or switched, which energises the LED circuit, and consequently it lights up. Once no presence is detected by the PIR, the LEDs will remain energised by the capacitor for approximately 30 seconds until the capacitor discharges. The time for which the LEDs remain on is determined by the capacitor and R1, which is labelled on here. Sorry, R2, which is labelled on there, of 100 kilo ohms. They are directly proportional to the time period. So, this can be worked out in theory that T equals 100 times 10 to the power of 3 times 47 times 10 to the power of negative 6, and that equals 47 seconds. In practice, we found the 407 microfarad capacitor to last approximately a minute. So we actually lowered that down to 100 microfarads, which lasted around 30 seconds. This is my Veroboard schematic. Although this was not compulsory, I found it completely necessary to do this in order to help with the soldering. I found a free software package called DIYLC on the internet, and I then transferred my circuit diagram straight over to this whilst looking at my breadboard prototype. This has helped me immensely through the soldering process. And here we have my final circuit. This was all tested and working beautifully. When it came to soldering onto Veroboard, I made several mistakes just due to the complexity and my lack of skill and knowledge using a soldering iron. I have, however, completed evidence of a video showing this circuit actually working. This will be demonstrated next. The final meeting with the client was successful. We discussed the total cost of materials, total cost of labour and the invoice total, which we accepted and signed off by the client. Cost of materials $49.90, which is slightly over. It's actually £19.90 over. Cost of labour, my labour, which took 8 hours work, £25 an hour, was £200. That brings it to a total invoice of £249.90. Throughout the entire project, there were several problems that had to be faced and overcome. I've already detailed some of these in previous slides, however, I will recap. My simulation software Yenka did not contain all the components needed for the circuit design, so I had to use a potentiometer and I had to use a Zener diode in place of a PIR and in place of my regulator. My lack of knowledge and understanding and experience building circuits on breadboard held me back greatly. I had to go online and find a website which gave me 3 basic circuits to work from. I bought the components to build these and it gave me a fantastic foundation for moving forward to building my actual circuit onto breadboard. When I was building my circuit onto breadboard, the first thing I started with was my LED circuit. When I connected these in series, I had them all connected across the same rung, and each positive and negative point, anode and cathode point of the LED, were all in the same rung. This caused a short circuit and the circuit didn't work. I had to go online to find out that it'd have to go across rungs in order to get it to conduct current properly. When I built the PIR circuit, I was unable to get transistor 1 and transistor 2 to amplify the signal, thus no voltage or current could pass, and the Zener was getting very warm. So the Zener diode was replaced and it was changed with a 7805 regulator. In doing both of these, in doing this one thing, it fixed that part of the circuit. Again, the circuit would not work at all when it was all in one board. It had to be split into 3 separate individual circuits, as detailed earlier. The circuit again would not operate when it was all connected back into a single circuit, so an LED was added onto the PIR section so that we could see for sure that the PIR was operating, and this helped troubleshoot the issue. The original idea of solar panels would not power the circuit as intended. I had to actually go out and buy my own trickle charge solar panel from Maplin and connect this with a custom built charger. This resolved the issue and allowed a battery to be charged and then power the circuit with 9 volts. I was unable to hand draw the Veroboard schematic on my diagram paper that I had, so I had to download the DIY LC software package which allowed me to come up with a perfect Veroboard schematic. When I was soldering, I was repeatedly producing really bad dry joints. I had to use a new tip, it was a screwdriver shaped tip, which allowed me to tip the solder onto it and then touch and then get the solder onto the board and allow for a little drip there to fill in. I was actually using a broken tip when I started my soldering and I messed up a few components. 2 of the components I messed up were my 7805 regulator and the most expensive part, the PIR. Both of them were destroyed. I had to buy new ones, and that came to a total of £12. For the next stages of the project, I need to complete my report by the 28th of May 2015 for my client. I must build a scale model for the shelter made out of wood or MDF. I must incorporate the circuitry into this shelter that I'm going to build. So some of the future improvements that I could come up with was the idea for like mood lighting, colour temperature. What that would do is have a thermistor somewhere that would detect like the cool air or the hot air, and based upon this could produce the colour of light to give you the sensation of heat or cold. So if it was a cold night, it would produce a nice red light, and that would give you the feeling, surroundings of hotness, warmth. The next thing I could think of was increasing the battery efficiency and the battery capacity. This would then allow less daylight to be produced in order to power the circuit successfully and get more energy back onto the grid. Also considered adding a dimming functionality to the circuit, so when there's no one around, it would go to dim first before going off completely. That could be achieved by adding additional capacitors in the circuit. The PIR detection range could be increased by adding multiple PIRs around the circumference of the roof of the bus shelter. And then finally, the circuit protection fuses could be added in there, or circuit breakers if needed, but it's only 12 volts, so it could be tiny little fuses could be added in there to make that circuit a wee bit more protected. I've now come to the end of my presentation, and I'd like to say thanks to Callum MacDonald for a continued support and approval throughout the project. I would also like to say thanks to Stuart Logan for his support with the design and calculations of the project. And finally, I'd like to say a special thanks to Gary Murray for his assistance in the build on breadboard and on Veroboard using solder. Thanks for listening.